An example from section 11.6 of Archimedes' principle, example 9, a swimming raft. The raft is made of solid square pine wood. Determine whether the raft floats in water, and if so, how much of the raft is beneath the surface. So they give us this nice picture here that shows the dimensions of the raft, the length, the width, as well as the overall height or thickness of the raft, right? This 0.30 meters. And so I tried to transcribe that up here. I'll stop the share so that you can see a little more. Here we go. So I drew my raft, the length, the width, the height, and I wrote down those dimensions, length, width, height. I also noted it's pine wood, which, what does that tell us? Why do we care that it's a pine wood raft? Is that just a good selling point? Now remember, anytime the material's mentioned, that's a clue. That's telling you the density. All right, so the pine wood, you can look in that table, 11.1, and find the density of pine wood. So a row pine, and it turns out it's 550 kilograms per cubic meter. Great. Anything else that we know here? There's something else that's implied in the picture, and that's, what is the raft in? Well, since it doesn't specify, once again, we can assume that the raft is in a fluid of water. In water, we can look up the density, but that is just the 1,000 with 4 significant figures, kilograms per cubic meter. And we could draw in the water on our raft too, to help remind ourselves that the raft is in a fluid. So what we want to figure out is, does our raft float? Right? And the other thing is, how much of the raft is potentially beneath the surface? So coming back over to our picture, if it does float, is it going to be the full thickness h underneath, or is it going to be some other amount? So I could just call that y, because why not? All right. So as I'm thinking about this, if I want to know if it floats, I think I first need to know how much the raft weighs, right? So, okay, let's look at the weight of the raft. We know weight is going to be mass times gravity. We don't have the mass of the raft, but we do know density is related to mass, right? Density is equal to mass divided by volume. So we can get mass by multiplying volume by both sides. So instead of mass, I'm going to fill in density times volume times g. Now, what density do we want to use here? Because we have 2 different densities. Glad you asked, right? Remember, this is about the raft and what the raft weighs. So that's where we're going to want to use the pine density. For the volume, this is going to be the total volume of the raft, right? So we could calculate that with our length times our width times our height. And this would be the volume of the raft. So we could plug that in, 4 meters times 4 meters times 0.3 meters. And if you calculate that out, you find that the volume of the raft is 4.8 cubic meters. All right, so now we have the volume of the raft, the density of the raft times g. We're in really good shape. So 550 kilograms per cubic meter times my 4.8 cubic meters, and we'll notice the cubic meters cancel there, so that's great, times g. 9.8 meters per second squared. All right, so if you multiply these out, you should get something on the order of 26,000. Now, what are the units here? Units are a little tricky. We said the cubic meters cancel, so you have kilograms times meters per second squared. Kilograms is units of mass, meters per second squared is acceleration, mass times acceleration, MA, that's our units of force, newtons. So now we know the weight of the raft. So we need to see, can the raft support, or can the water support this weight of the raft? So to do that, we can figure out the maximum buoyant force possible. The maximum buoyant force possible is going to be if the entire raft is submerged, right? That's displacing the most amount of fluid. So let's move this up a touch. There we go. So FB max is equal to if entire raft is displacing water. So what does that mean? Well, we know the buoyant force is equal to the weight of the displaced fluid. So we're going to use that. Buoyant force is equal to the weight of the displaced fluid. So the mass of the fluid times G. So now with this equation, mass of the fluid, when we plug in our density times our volume, we're going to be using the water quantities. So the density of water times the total volume of the raft is going to give us the maximum displaced water times G. So if we plug these in, we get 1,000 kilograms per cubic meter times the volume of the raft, that 4.8 cubic meters, times G, which is just our standard 9.8 meters per second squared. And so if you multiply those out, you end up getting 47,000 newtons yet again. And notice this 47,000 newtons is definitely larger than the weight of the raft. So because it is larger, the raft does float. FB max is greater than the weight of the raft. So that's great. That's our big picture idea here. Now, once we know that it is floating, that it's not sinking, then we can use that special extra case equation that we have. So I'm going to get another board for this. I'm going to hope you are not getting bored as I get another board. So because raft floats, we know that the buoyant force must just be equal to the weight of the raft. We don't need all that extra buoyant force. You know, it's 47,000 compared to 26,000. We don't need the extra 20,000 newtons of buoyant force. So we don't need our raft to be all the way at the water line. It can be sitting a little bit above that. So we need to figure out what our buoyant force actually is if it's less than that max value. So the weight of the raft we still know is our standard, what we calculated before, 26,000 newtons. That hasn't changed. But now when we go over to the buoyant force here, we're still going to use the density of water, but it's going to be the volume of the water displaced, not the entire raft's volume, times g. And so this volume of the water displaced, oh, we could almost see the picture there. I'll lower this. This is talking about the part that's just underwater here, right? And it goes out this way too. So that VW is equal to length times width still, the dimensions we already had, but now it's times y instead of times h. And we don't know what y is. That's something we want to try to figure out. So this means we could fill into this table with my density of water times my length times width times y, which is what we're solving for, how much it's submerged, times g, and that's equal to the weight of the raft, 26,000 newtons. So all we have to do is divide everything that's not y to the other side, and then we'll be home free. Now I will move this up again. So y is equal to 26,000 newtons divided by the density of water, 1,000 kilograms per cubic meter, divided by the length, which is that 4 meters, divided by the width, 4 meters, and don't forget the g, divided by 9.8 meters per second squared. With each of those terms, you should be able to calculate that this y value comes out to 0.17. And the units even do work out to come out to meters, believe it or not. You can check it. So a quick check for reality check, is this less than the overall height of our raft? Remember, our height of the raft was 0.3 meters, so this is indeed less than 0.3. So whew, it did work out. This is less than that. So the raft is about halfway into the water. And that's a good thing, right? If you're trying to play on this raft, you don't want to be right at the water line, or if you want to keep things dry on top of it, you'd rather have a little bit of give there. This way the raft too could support other people on top of it, not just the weight of the raft. So this demonstrates how we can use Archimedes' principle to set the buoyant force equal to the weight of the displaced fluid, however much fluid is displaced. And then if we know it's floating, we know the buoyant force must be equal to the weight of the object specifically, that special subcase. So we will wrap this up right there.